Hello, everyone. Thank you for having me here, and welcome to my talk. The title of my presentation is going to be called Transient Dynamics of Accelerating Turbulent Pipe Flow. My name is Byron, and I'm a PhD student at the University of Adelaide. Before I start with my talk, I would like to acknowledge my supervisors, Dr. Ray Chin and Professor Martin Lambert. So today we will have during this talk, we'll have a brief introduction about turbulent pipe flow and steady flow, and then I will talk the motivation related to this work. Later, I will talk to the numerical details of this of the simulations I ran, and finally, I will talk about wall friction in unsteady flows. So, why are we studying turbulent pipe flows? If pipes are such a simple geometry, it's just a cylinder. And we're still studying this problem because it's really hard to understand, because we have a chaotic, unsteady, anisotropic, and inhomogeneous flow. And this is when we have constant flow rates. This problem becomes more difficult when we have unsteady flow rates, which means that we're changing the velocity of the flow. So we can see unsteady pipe flows in everywhere, in everyday applications like in our homes, or maybe in industry, or even in transportation pipelines like the ones we use to transport oil, gas, or water. And we rely on pipes, even if we don't really think about it all the day, but we rely on pipes every day for several activities in our lives, such as these big pipe networks we have in cities and in industry as well. And because pipe flows are very important in our societies, during the last century we were able to develop some engineering models which are useful to predict the friction factor in terms of the Reynolds number. So here we can determine the friction factor based on the Reynolds number we have using a diagram like this one, the so-called Moody diagram, which is based on an equation called the Colebrook equation. However, these models are very useful to determine the friction factor or to predict the frictional drag, which is related to the energy losses in pipes, just for steady flows, which means constant velocities or constant flow rates. However, if we really think about it, most flows in industry are not steady. Usually they are unsteady because we have pumps or we have valves which are opening, closing, pumps starting up, pumps shut down, or modulation in the velocity of the pump. So the actual flows are not really steady. However, the three-dimensional physics of unsteady flows are still not fully understood. And that's what we're trying to tackle. So before showing us our work, I'm going to explain some literature. So one of the first attempts to solve this problem of unsteady flows was performed by Zielke in 1969, and he worked on laminar pipe flows. And Zielke came up with a very accurate model. However, most industrial flows are not laminar, they are turbulent. More recently, in the 90s and in the early 2000s, Brunoni and Barden Brown, they developed an unsteady friction model for turbulent flows. And this model is very good. It seems to work quite well, actually, for problems like water hammer or shock waves in train tunnels. But this model is applicable during very short time scales because they assume a constant or a frozen eddy viscosity. In other words, they're assuming that turbulence remains steady even if we accelerate the flow. which is not entirely correct. Now, further studies have been made in accelerating flows using experiments and numerical simulations. This is an experimental study by Greenblatt and Mose, and this is a study by he and Sedicki, and they tried to determine the physics. These are more fundamental studies. So they tried to determine which are the unsteady physics of accelerating flows. Greenblatt and Mose determined that unsteady flows have 3 unsteady phases, which are called the initial, the final, and the relaxation phase. On the other hand, he and Sedicki, in 2013, they ran a DNS of a turbulent channel flow. And according to their research, they determined that there are 2 unsteady phases based on the response of the skin friction coefficient and other flow statistics. And these stages are called pre-transition, which happens when the skin friction coefficient has a very dramatic decay, and the pre-transition finishes close to the minimum attained by the skin friction coefficient. The other one is the transitional stage, which is when we have a recovery in the skin friction coefficient, and this recovery is related to a generation of turbulence. So this is basically the study by he and Sedicki. And there aren't many more studies showing us more physics of unsteady flows. So this leads us to the motivation of our work, because we have right now a very limited understanding in unsteady flows. And these flows are very important not only in industry, but also, for example, when we have pulsatile flows in arteries, for example. So from a fundamental perspective, we want to understand these flow dynamics of accelerating and decelerating flows using direct numerical simulations. In this case, we're not going to do pulsatile flows. We will do just linearly accelerating or decelerating flows. And once we understand these flow dynamics from a fundamental perspective, we will try to propose a more accurate model to predict the unsteady friction during larger time scales. So, what's the method we used? As I explained before, we use direct numerical simulations. And to do that, we have used the 3-dimensional Navier-Stokes solver called NEC 5000, which is an open source solver developed in Fortran by Paul Fisher. And each spectral element was discretized using 7th order Gauss-Lobato legendary quadrature points. So we're using spectral element methods in this case. And for the time integration, we use a 3rd order backward difference game. And these are some of the results of the direct numerical simulations. So here in this plot, we can see that we're changing the bulk Reynolds number from an initially turbulent Reynolds number. So before time 0, we had constant velocity for a very long time. And then at time equals to 0, we ramp up the flows. So we accelerate the flow rate. Of course, the Reynolds number increases, and then we remain the velocity or the flow rate steady for a long period of time until we get again the universal loss of turbulence. We used to conduct these numerical experiments different initial, final Reynolds numbers, and also different acceleration rates. And we can see that the response in the skin friction coefficient in this case is similar to what we saw for he and Sedicki. And also it shows coherence in the way the skin friction coefficient responds. So it increases, as we can see in this black line. Skin friction coefficient has a very dramatic increase during the ramp up, then it peaks, and then it follows a reduction. And finally, it recovers and then remains steady. And that's the behavior of our skin friction coefficient. Now, this is the three-dimensional response of the turbulent eddies, which is interesting to analyze to better understand how turbulence propagates in time from a qualitative point of view. So what we have here is basically the flow mesh. This is the mesh we use to run the simulation. And these isosurfaces are the turbulent eddies identified using the lambda2 criterion. And the color is the distance from the wall. So when it's blue, these eddies are very close to the wall. And when it's red, it's far from the wall. So in this case, the flow the flow was accelerated from time equals to 0 up to 2 seconds. So we can see here the time. And after 2 seconds, we will realize that the velocity is constant. Now we want to see how turbulence is generated and how it propagates. So this video is telling us that at the beginning, turbulence is nearly frozen. We don't see many changes. However, after, we can see that some turbulence similar to what we see in the transition from laminar to turbulent are generated. And then the field is being populated with turbulent eddies, which propagate first near the wall. We can see from the color that the turbulent eddies are right now populating the near wall region, and then they start propagating towards the pipe core. So there's a diffusion of turbulence as well. And that's one of the delays we can see here. This is interesting to see. However, this doesn't give us a lot of quantitative information. So we need to study this from a statistical point of view. And some quantities we can analyze, for example, are these ones. So in the dashed colored line, I have the time evolution of the viscous stresses. And in the solid colored line, I have the time evolution of the Reynolds shear stress. Before I explain all these plots, I have to mention that differently from the work by He and Sedicki and Grimlat and Mose, we determined that there are 4 transitional stages, not 3 like Grimlat and Mose mentioned, or 2 as He and Sedicki. We determined that there are 4 stages, and we call the stages inertial, pre-transition, transition, and core relaxation. And we chose those names to be consistent with the previous studies in the literature. So in the inertial stage mainly happens when we're accelerating the flow during the early acceleration. And during this time, what we see in the response is that the viscous stresses grow a lot and very close to the wall. So basically, this is telling us, this gives us the reason why the skin friction coefficient has this non-linear growth we saw in a couple of slides before. Okay, so there's a very big growth in the viscous shear stress during this stage. However, some interesting thing here is that the Reynolds shear stress, which is related to the response in turbulence, has remained almost unchanged. We don't see important changes here in the Reynolds shear stress. And this is telling us that turbulence is frozen even though we have accelerated the flow. Turbulence doesn't respond as fast as we think. Then we have the second stage called pre-transition. And the pre-transitional stage is consistent with the observations by He and Sedicki, where we had a decay in the skin friction coefficient, and we can see that here. So the blue color is the time where the pre-transitional stage starts, and the green color is when the pre-transitional stage finishes. Basically, we have a decay in the viscous shear stress close to the wall, and it even undershoots the initial steady state. And we can see that close to the wall, at about y plus 15 or 20, turbulence starts responding here. And it's probably related to the small turbulent spots we saw in the previous video. Okay, so during the pre-transitional stage, what we have is a decay in the viscous forces or in the viscous stresses, and a very mild response in the Reynolds shear stress, or a very mild response in turbulence. Now we have the transitional stage, where we can see that we have a balanced growth between the viscous forces or the viscous shear stress and the Reynolds shear stress related to turbulence. So turbulence is responding at a faster rate during the transitional stage. Also, in terms of turbulence, it's interesting to note that it responds first close to the wall. So this is y plus 10, between 10 and 50, which is the near wall region of the flow. And then it propagates towards the core. Okay. And finally, we have the core relaxation stage, where we can see that the viscous stresses are nearly unchanged. Nothing happens in the viscous stresses, but the Reynolds shear stress is telling us that now the core or turbulence at the core is responding, and turbulence at the near wall region is nearly unchanged. So another way to understand this is by analyzing the viscous force and the turbulent inertia, which are some terms of the mean momentum balance. And the viscous force is just the gradient of the viscous stress in the wall normal direction. And the turbulent inertia is the gradient of the Reynolds shear stress in the wall normal direction. And we can see some similar behavior. In the inertial stage, we have this nearly unchanged response, the viscous forces. A dramatic change in the viscous forces and a nearly unchanged response in turbulence, which is consistent with this frozen turbulence we saw at the beginning of the acceleration. Now, during the pre-transitional stage, we have a very mild response in turbulence and a decay in the viscous forces. And at the end of the pre-transitional stage, we should be able to see something like this, these turbulent spots, and we have some characteristic structures of transition, which are these hairpin vortices, and also these elongated streamwise vortices. Now, during the transitional stage, what we have is a balanced growth between the turbulent and the viscous forces. During the transitional stage, what we will see, or a characteristic of this stage, is that we will see hairpin forests, which is also another transitional structure that we usually see also in developing boundary layers. And finally, during the core relaxation stage, we don't see important changes in the turbulent inertia and the viscous force, at least not close to the wall. But as we saw from the Reynolds shear stress, far from the wall, turbulence is still developing. Okay, so the core starts being populated by turbulent eddies during this core relaxation stage. Another way to understand this, and probably an easier way to understand this, is in a one-dimensional form. And we can use a tool developed by Fukagata in 2002, which is the so-called FIK identity. And Fukagata developed this decomposition, or this identity of the skin friction coefficient, to understand what are the different dynamic contributions into the wall friction or into the frictional drag. Okay. The identity developed by Fukagata is very general and is not entirely useful for our case. So we have to do some manipulations, and we came up with this modified FIK identity, which is useful for unsteady turbulent pipe flow. And here we can see that we have three important terms. The first term is the laminar contribution, which is 16 on the bulk Reynolds number, and this is defining friction factor. Now, the second term is the turbulent contribution, and the turbulent contribution is dependent on the mean Reynolds shear stress, which is a function of time and is a function of the wall normal direction or the radial direction. Okay, and this is in integral form. And the third term is the unsteady contribution, and we can see that the unsteady contribution is dependent on the radius, of course, but is also dependent on tau. And tau is the total shear stress. This is the result of applying the identity from one of our data sets. In this data set, we increase the bulk Reynolds number or the friction Reynolds number, if we want to see it that way, from Ari tau 500 up to Ari tau 700. And this is consistent also with the four stages we showed you before. So we have here the inertial stage, when there's a very dramatic growth in the skin friction coefficient, which is the black line. Then we have the pre-transitional stage, where the skin friction coefficient decays. The transitional stage is when we have a recover of the skin friction coefficient. And during the core relaxation, the skin friction coefficient doesn't give us any hint because it remains almost steady. But the other terms are telling us the rest of the story. So the red line is the unsteady term, the green line is the turbulent term, and the blue dotted line is the laminar term. So the laminar term just changed during the acceleration, so during this very short period of time, and then it remains constant. And of course it decays because there's less laminar contribution as we increase the Reynolds number. Now, the unsteady term becomes dominant during the inertial stage. It becomes very high, and it overcomes the magnitude in the turbulent contribution. However, as we stop accelerating the flow during the pre-transitional stage, it quickly decays and becomes less and less dominant. During the transitional stage, it continues decaying, and during the core relaxation stage, it progressively decays in a very long time scale until it becomes negative. And some people may be wondering why it becomes negative. Is because now what dominates this term is the pressure gradient. And in pipe flows, if we remember, the pressure gradient is negative. Now, the turbulent term, or the turbulent contribution, decays very quickly during the inertial stage. And during the pre-transitional stage, it remains nearly unchanged. However, it has a positive slope, so there's a slight increase in the turbulent contribution. But the most important increase in turbulence is during the transitional stage. It grows a lot here. And finally, during the core relaxation stage, we have a very slow and progressive propagation of turbulence from the wall to the core. And yeah, that's the fundamental understanding we have right now about unsteady accelerating flows. And this has been recently published in this JFM paper. Now, we want to use this fundamental knowledge to make it useful for engineering purposes. because it's good to talk about the fundamental physics, but now we need to think about the applications of this knowledge. So we believe that this knowledge can lead us to develop or can lead us to improve the current unsteady friction 1D models. And yeah, there is right now we have this model developed by Bardi and Brown. And this model, as we can see, comparing with the accelerating case, which is what I highlighted here. If we compare to an accelerating flow, we have this nonlinear growth in this part. Then we have the pre-transitional phase, the pre-transitional phase when we have a decay in the wall shear stress, which is also well predicted by the 1D model. But the 1D model fails to predict this growth of turbulence and then the core relaxation phase. So the 1D model is useful, according to this, is useful during the inertial and the pre-transitional phase, but it misses the transitional and the core relaxation stages. So what can we do? That's the question. And also some people may be wondering why we want to keep working on these unsteady friction models is because most people don't have access to supercomputers to run DNS simulations because it requires hundreds or thousands of CPUs to run a DNS simulation. And gathering all this data and analyzing and post-processing gets up several weeks or months. So for engineering purposes, we need to find something that we can compute in a few minutes or in a few hours at most. So now we ran a series of additional simulations besides the simulations we showed you before. And now we accelerate and also we run decelerating flow simulations. Why do we run decelerating flow simulations? It's because we want to get a more universal model which considers both scenarios. Additionally, we're going to analyze some differences between accelerating and decelerating flows. So here we have two flows, one accelerating and one decelerating flows. And below, we have the response in the wall shear stress. For the accelerating flow, we can see the response I showed you before. So this would be the inertial stage, the pre-transition, the transitional, and part of this is the core relaxation until it becomes fully turbulent. And from intuition, in the decelerating case, we would expect, or at least I would expect, to see a mirrored behavior. But we can see that decelerating flows do not respond in a same fashion as the accelerating case. So we can see that there are some differences. And also the core relaxation stage in a decelerating flow seems to take longer periods of time. So it's interesting, before getting to the statistics, it's interesting to see the qualitative behavior in time. So an accelerating flow or an initially turbulent flow, which is accelerated, has this behavior. So this is the typical low Reynolds number turbulence, or the wall shear stress at the wall. And this has this streaky behavior, and we have these typical streaks, which is the organization we have turbulence near the wall. But as we start accelerating, these meandering streaks start elongating. Okay, so they elongate and they become more stable. And at the end of the pre-transition, we will see these turbulent spots here. And these turbulent spots will later propagate throughout all the pipe, throughout the domain. And then we will look something like this. It will look like that. So we have more turbulence for an accelerating flow. For a decelerating flow, also in my mind, I was expecting the accelerating process, but in reverse. So I was expecting to see something like this. But we can see that the behavior is very different. So we start at a high Reynolds number turbulence. So these two, the snapshots T and E are very similar. But when we decelerate, what we can see first here is that we have big, very big regions full of negative wall shear stress. We can see the color, the purple color is less than 0. So we have negative wall shear stress in large regions of the flow, which means that we have a lot of flow separation. And this flow separation is related to adverse pressure gradients and inflectional velocity profiles. I'm not going deep into that, but it makes the flow unstable. After the flow deceleration, it seems that turbulence is being dampened, and finally we get our final steady state. A statistical way to understand this is to get the RMS in the wall shear stress, the root mean square of the wall shear stress in both directions, in the streamwise and in the azimuthal or tangential directions. The continuous lines are for the accelerating case and the dashed lines for the decelerating cases. So for the accelerating case, we can see that first there's an anisotropy. So the response in the streamwise direction, which is the black line, is different from the azimuthal direction, which is this gray line. So there's a kind of frozen behavior in the azimuthal component in the wall shear stress, and then it increases later. On the other hand, for the accelerating case, the wall shear stress in the streamwise direction starts responding very quickly. And of course, because the acceleration is in the streamwise direction. In the decelerating case also, there are some differences. So there's also this delay in the azimuthal direction as well for the decelerating case, but the time delay is quite different if we compare to the accelerating case. An interesting thing to see here is that if we see the streamwise fluctuation, is that it decays and it undershoots the final steady state, which is this dashed line. This dashed line is indicating as the final steady state. It undershoots, which shows us that the flow tends to relaminarize, and then it becomes turbulent again. So yeah, there are some interesting characteristics here. And this is the behavior in the turbulent eddies identified by the lambda 2 criterion. I'm not going to explain this plot in depth, but it's interesting to see the eddy viscosity here. The eddy viscosity, which was one of the parameters used by Barty and Brown to develop their 1D model, is telling us that for accelerating flows, the eddy viscosity is frozen actually for a very short period of time, you can see. And then the eddy viscosity responds with a very, very big delay. So for the accelerating case, what is interesting to see is that the eddy viscosity, after being frozen for a short period of time, decays, undershoots the initial steady state, and then it grows up almost linearly, and then it keeps fluctuating around the final steady state. For the decelerating case, the eddy viscosity overshoots the final steady state, which is telling us that the flow becomes a little bit more turbulent as during the onset of the acceleration. Then we have a decay in eddy viscosity, and it undershoots the final steady state for an important magnitude. And then turbulence starts recovering, and we attain the final steady state value. So again, to analyze the difference between these two flows, to characterize them and then develop a new model, we used the FIK identity again. But in this case, we're using the FIK identity in terms of the wall shear stress instead of the skin friction coefficient. It's not a big deal. To do that, we just multiply everything by 1/2 times rho UB squared, where rho is the density and UB is the bulk velocity. And yep, that's how we do it. And then we get similarly 3 terms. So the total shear stress as a function of time is equal to the laminar component, the turbulent component, and the unsteady component. And this is the result of applying the FIK identity. I'm not going to explain all the terms, but one important thing we can see here is that the unsteady term, which is the blue line in this case, calculated from the DNS data, has a very similar response to the 1D model by Vardy and Brown, which is what we have from the literature. So the unsteady friction determined by Vardy and Brown gives us a good prediction of the unsteady component from the DNS data. Now, for different accelerating and decelerating cases, we can see the same trend, is that the unsteady component by Vardy and Brown, which is the green line, agrees quite well with the blue line, which is our unsteady component from DNS data. And this is at a high Reynolds number. And at a higher Reynolds number, it seems to collapse a lot better than at low Reynolds number. And this is good news because usually engineering flows or industrial flows occur at high Reynolds numbers. And for the decelerating case, we can see that also the agreement is not bad, it's quite good. So now this is giving us some hints to start developing a model. So now we want to predict the wall shear stress as a function of time. Okay, and this wall shear stress is the summation of these different components we have here. So let's see what can we do. Let's start from the easy part. So the laminar component is very easy to determine because the laminar component is just a function of known quantities such as density, viscosity, and the pipe radius, and the change of bulk velocity in time. So as long as we know the time dependence of the bulk velocity, we can predict this laminar term. So for this one, we don't need DNS data. We just need to know the bulk velocity as a function of time. So that's why I'm ticking here, is because we can calculate easily that component. The other component we need to know is the unsteady one. And the unsteady one is a little bit more tricky because this one depends on the mean Reynolds shear stress and also depends on the viscous shear stress. And that becomes more difficult. However, as I explained before, the Vardy and Brown 1D unsteady friction model gives us a good prediction of this term. And as a result, we can approximate the unsteady component by using the Vardy and Brown method. The last term we need to calculate is the turbulent component, which is this gray line. And to be able to predict this one, we need to know the Reynolds shear stress, the mean Reynolds shear stress, which is a function of the wall normal position and also is a function of time. And unfortunately, we cannot predict that using analytical methods because we should be able to solve the basically turbulence. And we go back to the closure problem of turbulence, which doesn't have solution. Yeah, if I would be able to find a solution, I would be a millionaire because there's a Millennium Prize for this one. So, yeah, I cannot solve that, but what we can do is to use the series of data sets we have from DNS simulations and try to find an empirical correlation. I'm not going through all the math we use to find the empirical correlation, but what I can mention is that we realized that the turbulent component follows a logistic function. So this is the model we developed from that. So this is the Vardy and Brown correlation. This is the the laminar component. This one is an additional term we're calling the steady component. And this is the turbulent component, and this is the logistic function. Okay. And after applying, these are in these plots, we can see the results of applying this equation. So the black line, the black continuous line, is the DNS data. So the wall shear stress computed by using DNS simulations. And the diamond is the result from this model. So we can see that in different cases, the model agrees quite well with the DNS simulation. And these terms here, the red, the blue one, and these dashed lines are each one of the terms we have computed from this simulation. So what we see here is that the model agrees, in this case, quite well with the DNS simulation. It's important to mention that this model is good right now for rapidly accelerating or rapidly decelerating flows. Probably some of the constants we have in this term need to be tuned a little bit more as we get more DNS data sets. Probably would be good to test the same thing at a lot higher Reynolds numbers with milder accelerations and decelerations. Also, it would be interesting to see what happens when we have rough pipes, because our simulations are for smooth pipes. But I think it's a good start to get a more universal unsteady friction model. This study has recently been submitted to the Journal of Hydraulic Engineering. Same authors here. And actually, we got recently a letter from Alan Vardy, which is the author of the most popular unsteady friction model we have now. And he read our manuscript, and he's very happy with the results, and he wants to contribute with us. So that's good news for us. So thank you for your time. And please let me know if you have any questions.